Welcome to this video on loop optimizations in compiler design. Today we will explore key techniques for optimizing loops illustrated with simple C++ code examples. In a previous video, we discussed local optimizations, which are confined to individual basic blocks within a control flow graph. Loop optimizations, however, fall under global optimizations because they analyze the control flow graph across a broader scope. By identifying loops and their dependencies across multiple blocks, the control flow graph enables powerful transformations. Why loop optimizations? Loops are often the most computationally intensive part of a program. Optimizing them greatly enhances program speed by reducing execution time and improving overall efficiency. Furthermore, loops disrupt normal program flow. Optimizing them can increase parallelism, pipelining, and improve cache and memory utilization. Let's now discuss 5 key loop optimization techniques with examples. The first and most commonly used optimization is loop unrolling. Instead of iterating one step at a time, we increase the loop step size by duplicating the body of the loop. By reducing the number of iterations while maintaining correctness, loop unrolling decreases loop overhead and improves performance. Here is an example. Consider a loop that runs n times where n is unknown. Using loop unrolling, we reduce the number of iterations to half. This modified code works for both odd and even values of n. When n is even, the unrolled loop processes all elements. When n is odd, the last element is handled separately by the conditional code after the loop. The second technique we will discuss is loop invariant code motion. This technique moves calculations that do not change within the loop to outside the loop. For example, consider the code which adds the value of x times y to each element of an array. Notice that x times y is a constant that could be computed once outside the loop. Using loop invariant code motion, instead of calculating x times y n times, we calculate it only once, making the program run faster. The third technique is loop fusion. Recall nuclear fusion from physics, where we combine 2 or more atoms to make a single atom. Our sun gets its energy using nuclear fusion. The same idea can be applied to loops. If 2 or more loops iterate over the same range, we can combine them in one loop to reduce overhead. Here is an example of 2 loops that iterate over the same range. There could be code between the loops, but as long as it does not depend on the variables being updated inside the loops, we can perform loop fusion. The resultant code after loop fusion has half the number of iterations and will run faster. While loop fusion combines 2 loops to reduce overhead, loop fission split a loop when there are different data sets involved, improving cache locality and performance. Both techniques aim for optimizations, but they apply to different situations. Fusion is useful when combining independent loops working on the same datasets, while fission is beneficial when a loop operates on different datasets that can be handled more efficiently separately. The goal of loop fission is to improve cache efficiency by focusing on smaller relevant datasets, whereas loop fusion aims to reduce loop overhead by combining related operations. Here is an example. The original code has loop operating on two different arrays. Breaking it into two loops allows each array to be cached and processed separately. Using loop fusion, we split the loop into two separate loops for different data sets, improving cache management. The fifth loop optimization is loop unswitching. If a condition inside a loop does not depend on the loop variable, we can move it outside the loop. For example, in the original code, we perform two different operations depending on a flag. Each time inside the loop, the condition is checked, which is unnecessary. Using loop unswitching, we take the condition outside the loop. Although we write the loop code twice, only one loop executes at runtime, making the code faster. These are the 5 commonly used examples of loop optimizations. Modern compiler automatically perform many of these, but understanding them help you write better performing code and appreciate how your compiler works. Thanks for watching this video. Do not forget to support this channel. See you next time. Bye.